Chapter 17, we're going to take the concepts from Chapter 15, Le Chatelier's principle, and we're going to mush them together with the equilibrium concentrations that we learned in Chapter 16 using the ICE table. And we're going to specifically apply that to acid-base equilibria as well as solubility equilibria. Places to focus would be buffer solutions, titrations, just a little bit on solubility equilibria. It's very easy to do. So after you get the ICE table and stuff down, the solubility equilibria is very easy. This is a conceptual section, knowing the factors that affect solubility, and then we will separate ions using differences in solubility. So just as a review, Le Chatelier's principle states that a system at equilibrium will shift in response to being stressed. Now we can add a reactant or a product in order to apply stress. So for example, if we have this acetic acid equilibrium here, and we start with an initial concentration of 0.1 molar acetic acid, and we work out the ICE table, we can find the concentrations of our equilibrium mixture, as well as the pH of this equilibrium. And of course, that is based on the concentration of the hydrogen ion. Now, if we add sodium acetate to this solution, what would happen to our equilibrium? Well, sodium acetate in water does break into its ions, sodium and acetate. So what we are doing is increasing the concentration of our acetate. And when we do that, the equilibrium is then driven towards the reactant. It shifts left. Remember, it shifts away from an addition. So when we work this example, if we're going to determine the pH at 25 degrees of a solution prepared by adding 0.05 moles of sodium acetate to 1 liter of 0.1 molar acetic acid, assuming no addition of that the addition of sodium acetate will not change the volume. So we're still working with 1 liter. That's why that is there. We need to determine the pH. So we'll start with this ICE table. Our initial change in equilibrium table is called an ICE table. So here we have our weak acid, acetic acid, and that reacts, this is just the equilibrium of the weak acid. We have our hydrogen ion and our acetate ion. But in this case, we start with an initial concentration of our acetate ion. And that initial concentration is equal to the concentration of our sodium acetate. Remember, our sodium acetate breaks up, as we saw in the last slide, breaks up into sodium and acetate ion. Well, here is your acetate ion. So that is why we have an initial concentration here. So that changes our equilibrium mixture like this. So when we do those calculations, then you need the Ka, and if you don't have it memorized, it's absolutely fine. It is available to you in tables. So the Ka of acetic acid is 1.8 times 10 to the negative 5. Now remember, this is the concentration of the hydrogen ion times the concentration of the acetate divided by the concentration of the weak acid. In this case, acetic acid. I should make that specific. So that is what these are. These are your equilibrium concentrations of these specific portions. Now, because we expect X to be small, we can simplify and just work the problem. 1.8 times 10 to the negative 5 equals 0.050x divided by 0.010. Do that arithmetic and find that X is approximately, there it is. X is 3.6 times 10 to the negative 5. Now, on the equilibrium table on the previous slide, the concentration of the hydrogen equals X. So in order to find the pH, I just need to take the log of this value because it is the concentration of my hydrogen, and the pH is 4.44. Now, a buffer solution is a special case with a weak acid, and it's a case of a weak acid and its conjugate base, and that resists a pH change. That is the definition of a buffer. So in this case with acetic acid, we can make a buffer solution by having an acid and a conjugate base. The acid will react with any additional base in order to resist the pH change, and the conjugate base will react with any additional acid in order to resist that pH change. So if we're going to calculate the pH of a buffer, containing 1.0 molar acetic acid and 1 molar sodium acetate, then all we're doing, what's different between this chapter and the last chapter, is we're starting with more than one initial concentration. After that, the calculations are very similar. So we're going to remove some amount of reactants X. So our equilibrium concentration of our acetic acid is 1.0 minus X. And then we're going to add some amount of hydrogen ion or hydronium. If you're still using that connotation, that's fine. So we're going to add some amount of hydrogen ion X so that its equilibrium concentration is equal to X. We will also be adding to the acetate ion. That's important to see. We will be adding to the acetate ion in some amount X. So to calculate the X value, we set up the Ka expression, and this is set up the same way we did it in the last chapter. This is the concentration of the hydrogen ion. This is the concentration of the acetate ion, and this is the concentration at equilibrium of our weak acid. So as you can see, it is set up the same. Now, because this value, the initial concentrations, are more than 1,000 times greater than my Ka, I can simplify this. So I will, and then we can solve for X, and X is equal to the concentration of the hydrogen ion, which in this case is also equal to the Ka, the value of the Ka. So the pH is equal to the pKa here, 4.74. We'll get to pKa in a minute, don't worry about that yet. Calculate the pH of the same buffer after the addition of 0.10 moles of hydrochloric acid. Now, the hydrochloric acid will react with the conjugate base, the acetate ion, and it will make more weak acid. So we have to look at this as if the acetate is being consumed. This is being removed, and it's being removed in the amount of the strong acid that we used. Now we are removing, or we are adding, that amount to the weak acid. So this is where students get a little fuzzy. So make sure that you understand conceptually what's going on here. We start with 1.0 moles of our weak acid. We also started with 1.01 moles of our acetate. By adding the strong acid, we remove some of our acetate, so now we're at 0.9, but we have increased the weak acid, so now we're at 1.1. So now these are our initial concentrations that we will use to calculate. We are still going to be removing some amount of our weak acid X, and we will still be adding that amount X to both our hydrogen ion as well as our acetate ion. So then we do the very same calculation. Again, these calculations should look very familiar, and you should be familiar with them right now. And then we can calculate the X, but in this case, again, we can simplify because we are more than 1,000 times different here. So the hydrogen ion concentration equals 3.6 times 10 to the negative 5, or there's a pH of 4.66. Now the original buffer had a pH of 4.74. Notice how adding that strong acid didn't change the pH of the buffer all that much. Now we can also calculate the pH of a buffer by using what's called the pKa, and this is called the Henderson-Hasselbalch equation. The pKa is simply the negative log of the Ka. So this is a p function just like pH. Remember, pH equals the negative log of the concentration of the hydrogen or hydronium ion. So this is a p function. You can just assume a p function is the negative log of whatever it is you're looking at. And you can derive the pH by taking that pKa and adding it to the log of the ionization. So we have the concentration of the conjugate base. So in this case would have been the acetate ion, and the concentration of the weak acid. So we're looking at that ratio, the ratio of concentration. So basically, how much has it ionized? So for example, it's always easier to explain some of these things or hammer them in with examples. If we start with 1 liter of a buffer, That is 1 molar in acetic acid and 1 molar in sodium acetate. And we calculate the pH after addition of 0.1 moles of sodium hydroxide. And we assume that the addition does not change the volume, just to keep it as easy as possible. Then what we need to recognize is that the added base will react with the acetic acid component and will convert the OH to water. So what I'm looking at is I have my acetic acid, and I'm going to leave off the phase tags here, and my base. That's really the important part, and this is going to go to completion. This isn't something that's going to equilibrate because we do have a strong base. And we will end up forming liquid water. There I will put the phase, because the hydrogen and the hydroxide will join together to form liquid water, and we will form more acetate ion. So here we started with 1.0 capital M molar of acetic acid, and we also started with 1.0 molar sodium acetate, but now we're going to remove 0.1 moles, so we have 0.9 to start with for our initial concentration, and we're going to add 0.1 moles here. So for 1.1, there we go, moles of our acetate. So for our initial concentration of our acetate ion, here we go, we're going to look at the ratio of acetate to weak acid, which in this case we're looking at 1.1 over 0.9. Now remember, what we're going to do with the Henderson-Hasselbalch equation in order to calculate this pH is we're going to look at the log of that, and we're going to add that to the pKa. Well, in order to find the pKa, you must know the Ka, and the Ka of acetic acid is 1.8 times 10 to the negative fifth, so the pKa is actually 4.74. So if I work this arithmetic and take 4.74 plus the log of this ratio, I end up with a pH equal to 4.83. Make sure you know how to manipulate your calculator so that you get the same answer. A rule that is very often overlooked is that buffers must have the conjugate acid base concentrations within a factor of 10 of one another. So the ratio must be between 10 and 0.1. This is something very often overlooked, and I would very strongly suggest that you write this down somewhere so that you have it available to you. The pH of a buffer cannot be more than 1 pH unit different than the pKa of the weak acid it contains, because the system simply is not going to be able to handle an overload of acid or base. It can handle small amounts and resist change. So to make a buffer that has a specific pH, if we're targeting a pH range, we need to pick an acid whose pKa is close to that pH, and that way you will get your desired pH range for your buffer. So if you substitute the pH and the pKa into this equation here, then you will find the necessary ratio here. So if we're going to select an appropriate weak acid from this table to describe how to prepare a buffer with it of pH of 9.5, we should start by finding something that has a pKa about what the pH of our target. So we're going to look down here. We're going to look at HCN or C6H5OH. This is hydrocyanic acid and phenol. So if I start with the first one, hydrocyanic acid, and remember your Henderson-Hasselbalch equation, pH equals pKa plus the log of the ratio. I'm looking at A minus over HA. Then I'm going to substitute in my pH, my desired pH, and my pKa, 9.31, and I'm going to solve for this ratio. Now when I do that, and this is specifically, I ought to be specific here, this is specifically for cyanide over hydrocyanic acid. So I get the ratio of cyanide to hydrocyanic acid is equal to 10.48. Well, that's a little bit more than 10, so I don't think we're going to be using hydrocyanic acid. So let's look at phenol. Again, I want 9.5 and my pKa is 9.89. I'm going to look at the log of my phenolic anion and phenol. And then when I solve for that, I get the ratio of my anion to my weak acid is actually equal to 0.41. In this case, this is within our range. Therefore, I would use phenol for that buffer. And I would use a concentration of my phenolic acid if I declared my initial concentration of phenolic acid or phenol to be 1 molar, then I would need the concentration of my conjugate base to be 0.41. In the laboratory, one way to measure the concentration of an unknown acid or an unknown base is with a technique called titration. And this is actually just an acid-base reaction, but it's a controlled acid-base reaction. And the reaction between a strong acid and a strong base always forms water and a salt. Now, you have to pay attention to the stoichiometry, but the net equation here is that hydroxide is reacting with hydrogen in order to form liquid water. So when you have this titration, what you're doing is you're starting with uh, an unknown concentration of acid usually, and then you're going to titrate it with a known volume of base. In this case, we're giving the example of a strong acid, strong base, and we know everything about it. But what we're showing here is as you add base to your acid, your pH changes ever so slightly here until you get close to what is called the equivalence point. The equivalence point is when there are equal molar amounts of acid and base reacting, and that is where you have the most dynamic portion of pH change when you have a strong acid and a strong base. Now, when you're working with a weak acid and a strong base, you have to take into account the fact that the weak acid has a little bit of its own equilibrium going on. So the initial pH, you can still see at the equivalence point, you've got this dramatic pH change. And the curve looks similar here, but it's more squished. And it's more squished because we're starting at a higher pH. And that initial pH, we can determine the pH at any point on the titration curve, but that initial pH is determined by the ionization of the acetic acid. And this isn't new, this is what we've been doing for the last 2 chapters. But the initial pH is the initial equilibrium of the acetic acid before any base has been added. After we add some of the strong base, however, now we need to look at the acetate ion and the weak acid concentration. So if we've added 10 milliliters of hydroxide, we can calculate the moles of hydroxide acid or hydroxide added, not hydroxide acid. Remember how molarity and volume are related and how to convert moles. Remember that if we start with 10 milliliters, and you should be able to convert between milliliters and liters very quickly, and you multiply that by your 0.100, and that's moles per liter, and I'm looking at the NaOH specifically, then the liters cancel out and I get moles. Remember those kinds of calculations. That it is expected that you do know how to do that. So you should be able to calculate the moles of hydroxide added. Now, when you add that hydroxide, you are removing the weak acid. So we started with how many moles of acetic acid? Well, I would take my 25 milliliters and multiply it by, I'm trying to use the book's notation and I'm reverting back, multiply it by the concentration that's in moles per liter so that my liters cancel out. I start with 2.5 times 10 to the negative 3. That's how many moles I have. Now, your book is using millimoles here, but isn't being clear about it. This is millimoles. Remember, 1,000 millimoles are in 1 mole. And they're doing this conversion back and forth, and it's kind of making me a little crazy, but I'm going to roll with it as best I can. So what we're looking at here is taking away the amount of hydroxide added from the initial concentration of the acid, because from this equation we can see that that hydroxide is taking that acid away. And what it's doing is adding to the acetate. And from there I can use the Henderson-Hasselbalch equation to calculate the pH. So the pH equaling the pKa, which has not changed, it is 4.74 for acetic acid, plus the log of 1, which is the concentration of my acetate here. This is CH3COO minus, over the concentration of my weak acid. This is the acetic acid. And that equals the pH 4.56. So at any point in the titration, you can calculate the pH by using the Henderson-Hasselbalch equation. Now at the equivalence point, all of the acetic acid has been neutralized. Now we've added 25 milliliters of hydroxide, which is, again, this should be millimole, which is 2.5 millimoles of hydroxide added. We have removed all 2.5 original millimoles of acetic acid. We have produced 2.5 millimoles of acetate. We have a total volume now, because we started with 25 milliliters of acetic acid. We just added 25 milliliters of hydroxide. We have a total volume of 50 milliliters. So now we have to recalculate our concentration. You must use the total volume to calculate the concentration. So now, using that as an initial concentration, we are going to change that concentration because we are in an equilibrium. And we can calculate then the concentration of our hydroxide ion by using the Kb. I need you to see that this is the base form of the dissociation of the acid, because it's flip-flopped. We have flip-flopped the acid in the base, or the acid in the conjugate base. Because the conjugate base is on this side and the weak acid is on this side, on the product side, we must use the Kb expression, the Kb constant. Remember, Kb is related to Ka. Ka times Kb equals Kw. So for the acetate ion, Kb is 5.6 times 10 to the negative 10. In the Kb expression, the concentration of the hydroxide ion times the concentration of the weak acid divided by the concentration of the weak acid's conjugate base, the acetate ion, equals this expression. Now, because our initial concentration and our Kb in this case are more than 1,000 times different, we can simplify. So when you solve for x in this case, x is the concentration of the hydroxide ion, which is 5.3 times 10 to the negative 6. You could then calculate the pH, and from the pH you can calculate the you can then calculate the pOH, and from there calculate the pH. Remember, pH plus pOH equals 14. So you see, this chapter really brings in all of the concepts from the last 2 chapters. So it's really important to have a strong foundation. Now, after the equivalence point, after you have used all of the acetic acid and it has been neutralized and there's nothing left to neutralize that strong base, then the pH is going to be dependent on that strong base. So looking at these numbers here, if you've added 30 milliliters of your hydroxide, but this was the equivalence point, this is where we had no acid remaining, then what we have is the excess amount of hydroxide and the total volume. That's what we're going to be using to calculate the concentration of hydroxide. And then from the concentration of the hydroxide, you can calculate the pOH, consequently the pH. Again, this is after the equivalence point. After the equivalence point of a weak acid and a strong base, after we have used up all of the acid, the pH is purely dependent on the excess amount of hydroxide that has been added. So after 35 milliliters, Then we've added 3.5 millimoles, and we have an excess of 1 millimole because 2.5 has been taken up by the equivalents, by the, where is it? There it is, by the acid. So because the acid chewed up 2.5, we have an excess of 1.0. We have a total volume now of 60 milliliters. You have to keep track of your volume as well, because concentration is not only dependent on the amount of solute, but also the total volume of the system. So then we can calculate the pOH purely based on the concentration of the hydroxide. Remember, pOH equals the negative log of the concentration of the hydroxide. That's all we're doing here. And then from there, pH plus pOH equals 14. And that's how we're getting the pH for that. So if we're going to work an example, calculate the pH of a titration of 50 milliliters of 0.120 molar acetic acid by 0.240 molar sodium hydroxide. Let's start with A, the addition of 10 milliliters of the base. The very first thing I want you to do is write out the chemical equation. So we have our acetic acid and our sodium hydroxide, and that will react to form, with a little bit coming back, water and sodium acetate. Now the sodium acetate, if I ignore the sodium here and just look at the ions, this is my conjugate base. Okay, so this is my weak acid, and here is my strong base. Now this is a one-to-one relationship, and that's all that we're doing right here, so you don't have to worry about stoichiometry quite yet. But to calculate the pH, I need to look at how much of everything I have. I currently have, oh, here we go, 0.50 liters times 0.120 moles per liter. Not sure why that erased. So, and to be consistent with your book, I'm going to actually just use the millimoles. And that would be 50 milliliters. That would be 6.00 millimoles of my weak acid. Now for my hydroxide, I have 10 milliliters of base. So I need to look at my 10 milliliters, and my 0.240 is my concentration. So for my hydroxide, I actually start with 2.40 millimoles of hydroxide. And I start with none of my acetate. So what happens is my strong base is going to be all used up. So I'm going to remove 2.40 millimoles of my weak acid, and I will add my 2.40 millimoles to my conjugate base. So I end up having 3.60 millimoles of weak acid, no hydroxide left to speak of, but I do have 2.40 millimoles of my acetate. Now, what we're asked to do, however, is to calculate the pH. So I'm going to look at this with the Henderson-Hasselbalch equation. pH equals pKa plus the log of the concentration of the conjugate base, which now we have 2.40 millimoles. It's 2.40 millimolar. And just to be thorough and consistent, I'm actually going to put that over the total volume. So that's going to be 60 milliliters divided by 3.60 over 60 milliliters. Now your book doesn't do that because those factors do cancel out. However, just to be consistent, I'm going to do it this way to try to get you used to the idea of keeping the total volume in mind. So I get that that particular part is equal to a negative 0.18. The pKa of acetic acid is 4.74. Therefore, the pH at this point is equal to 4.56. For B, again, we need to keep the acid-base reaction in mind, forming water and our acetate ion. After we're still going to start with our 6 millimoles. And we're still going, but this time instead of having 2.4 millimoles of our base, we start with 25 milliliters of base. So that means we also have 6.00 millimoles of sodium hydroxide. Now I get that by taking my 25 milliliters and multiplying it by my concentration of base, 2.240, and then I get a answer of 6 millimoles. So this is the equivalence point. And at the equivalence point, we have the same number of moles of acid and base. So we are completely consumed. And we have added 6 moles here. Now, because we're at the equivalence point, now we need to look at the concentration in terms of total volume. So here we have a total volume of 75 milliliters. Now that makes the concentration of our acetate ion 0.08 capital M molar. Now this is our acetate ion. And here we go, 0.0800 capital M molar. Now what we have here is the KB equation, the base dissociation. So I'm just going to write this off real quick because this is where you use the base equation once you hit the equivalence point. So we have our initial concentrations here. We start 0 and 0. Remember, water doesn't count, so this is initial. The change is going to be some amount x. We're going to add x to our products. So the equilibrium, 0.08 minus x plus, oh, I don't need the plus there, x and x. Remember Kb for your acetate ion is going to be 5.6 times 10 to the negative 10. We're going to put that equal to x squared over 0.08 minus x. We're going to simplify because our initial volume is more than 1,000 times greater than our Kb value. So I can solve for x, and in this case, I get an x value equal to 6.7 times 10 to the negative 6 capital M. Now that x value is equal to the concentration of my hydroxide ion. So in this case, I'm going to take my POH because that is what is easiest for me. If you would prefer to calculate your hydrogen ion concentration from this, you go right ahead. So I take my 6.7 times 10 to the negative 6, take the log of that, and I get a POH of 5.17. Now that makes my pH then 8.8. I get 8.83. Now for a strong acid weak base titration, you see the titration curve looks opposite because what you're starting with is the base. So you're going to start with your pH much higher. Now in this case, we're going to titrate 25 milliliters of a 0.1 molar ammonia solution with a strong acid, a 0.1 molar hydrochloric acid. Now we still have our equivalence point and our area of a whole lot of pH change right here. And the equivalence point in this case will be less than 7. And it will be less than 7 because remember, when you have your ammonia with water, we end up going to an ammonium ion. Why does that erase? And hydroxide. Now this ammonium ion here ends up acting as a weak Bronsted-Lowry acid. Remember, when we flip-flop that, we can have hydrogens being produced and ammonium. This is a weak base. It's called a weak base because we are in an equilibrium. Now, if we're going to calculate the pH at the equivalence point, when 25 milliliters of a 0.1 molar ammonia solution is titrated with a 0.1 molar hydrochloric acid solution, you have to know the relationship between ammonia and hydrochloric acid. Now, ammonia plus The H from hydrochloric acid, remember this is a strong acid, so it completely dissociates, and the chlorine doesn't really have anything to do with what we're doing. When you have the hydrogen react, what you end up with is the ammonium ion. Now that ammonium ion is a weak Bronsted-Lowry acid, and at this equivalence point, all of the ammonia has been converted to the ammonium ion. So we have to determine the concentration at the equivalence point using the Ka. Now the original solution, we have to find out how many millimoles of ammonium ion we have according to the original solution. And at the equivalence point, we have the same amount of hydrochloric acid being added. And the volume is 25 milliliters. Now that seems to be intuitive for a lot of students because we're working with the same molarity. It's a one-to-one relationship, so we must have the same volume. So with 25 milliliters here, we're starting with our 0.05 molar of our ammonium ion, and that is found by taking the moles that we had and dividing it by the total volume. Remember, total volume leads us to our concentrations. So we're starting with that amount of our ammonium ion. And when this forms its equilibrium, we have no ammonia because we're at the equivalence point. It's been removed initially. And we have no hydronium ion either. Now, to find the equivalence, we need to change our initial concentrations by some value x and solve using the standard equilibrium expression. In this case, we're using the Ka of ammonium. And the Ka, remember, is the Kb, the reciprocal of the Kb times the Kw. So Kw divided by Kb. And we find that here, in order to solve for x, to find our hydrogen ion, and here your book is using it interchangeably as well, the hydrogen ion concentration, which is also the hydronium ion concentration. So from there we can find the pH as the negative log of that value at 5.28. Now the equivalence point can be visualized by using what's called an acid-base indicator. An indicator is a weak organic acid that is one color in an acidic situation and another color in a basic situation, or at least one color on the more acidic realm and another color on the more basic realm. For example, methyl red has a area of indication, I suppose, between a pH of 4.2 and 6.3. It's not exactly basic, but it's more basic than 4.2. Where phenolphthalein, which is typically what we use in the general chemistry laboratory, has a range of 8.3 to 10. Now, phenolphthalein, just for those of you who are interested in the medical field, phenolphthalein is also used as the active ingredient in X-Lax, or at least it used to be. So acid-base titrations, the indicators can give you a wide variety of colors. This is actually an example of a bromethymol blue. So here are some acid-base indicators. You do not need to memorize this, but you might be asked to pick which indicator to use given the pKa of an acid, and the answer would lie in the pKa being approximately equal to or involved in the pH range. So which indicator would you use for acid-base titration shown in figures 7.3, 7.4, or 7.5? Well, you need to have access to those figures first. So here is 7.3, and this is a strong acid, strong base. pH range from about 4 to 10 would be ideal. So we need something that's going to change color around here. So looking back, 4 to 10, we would be looking for something that, depending on the application, like what pH are you actually looking for? I mean, most of these are going to work for you. I wouldn't necessarily use something like thymol blue because it's out of the pH range. We're looking for something between 4 and 10. And I wouldn't necessarily use bromophenol blue because the pH range I need just starts, I can't find there we go, just starts where my pH range starts for my period of dynamic pH on my table. And I also wouldn't use phenolphthalein for this application. So to get back here, here is my period of great pH change. So I need something that's going to change in here. Now for B, this is the second figure that we're looking at. And so we're looking for a pH change between around 6 and I don't know, around 10. So 6 to 10. And of the ones that we were looking at in that table, so now we're looking at something here. So we're looking at bromethymol blue and cresol red. It's possible to even use phenolphthalein for that instance. And for figure 17.5, we're looking at the steep part of the curve, and that happens to be between 8 and 3. So I would be looking, if I go back to my table, 8 and 3, I'm looking at something, I might use cresol red depending on exactly where I want to hit that color change, but in a real life situation, I would not. I would say cresol red is just, it's too close to my endpoint. Now, quantitative predictions about how much a given ionic compound will dissolve is possible, and that's using the solubility product KSP. Notice how all of these product constants are a K value. For example, something like silver chloride. Silver chloride is called an insoluble compound. The reality is a wee bit of it does solubilize. It's not so much that we can call it a soluble or even partially soluble compound, but it has a KSP value associated with it. And that KSP value, notice here, can be pretty darn small. Remember, the larger the negative exponent here, the smaller the number is altogether. So molar solubility is the number of moles of solute in a saturated solution, so moles per liter. Now the solubility, just to give you some keywords here, the solubility is the number of grams of solute in 1 liter of a saturated solution. So to calculate the molar solubility, we need to look at an equilibrium table, fill in what's known, and determine the unknowns. Now this is a really, really small table, but this is table 17.4 in your book, and it lists a number of KSP values. Now the silver chloride that I mentioned before, and we call silver chloride an insoluble compound, but the reality is just a wee bit of it does solubilize. It has a value of 1.6. I think that's times 10 to the negative 10. It's really hard for me to read on my screen. So we call it an insoluble compound, but just a little bit does solubilize. So looking at another example of silver bromide. Silver bromide, the KSP is 7.7 times 10 to the negative 13. So if we're going to calculate the molar solubility, we start with some amount of silver bromide, and then we have none of our products. Now, because silver bromide is a solid, it does not enter into the KSP, the equilibrium expression, or the change in concentration, because we're going to have a little bit of the solid. So we're going to increase that by an amount, and now your book is using S for some reason, and that increase can be related to the KSP value. Now the KSP value is then worked out in a very similar manner to all the other KEQ values that we have been looking so far, where the KS or the S value is now equal to the concentration of each of these ions in solution. And you see this is a very small number. So we can calculate the molar concentration based on the molar mass of our solution. So we calculate our S value, that is the concentration. We then convert those moles to grams, so now we have grams per liter, and this is called the molar solubility of the compound. So if we're going to calculate the The solubility of copper hydroxide in grams per liter. Again, we're going to refer back to that big table, and that table is on page 739 of your textbook. So I'm looking for copper 2 hydroxide. Copper 2 hydroxide is listed with a KSP equal to 2.2 times 10 to the negative 20. Now, copper hydroxide will break up like this. We will end up with copper 2, and this is aqueous, plus 2 hydroxide. Again, I'm leaving the phases off. So what happens is we start our initial change equilibrium. We start with zeros. We will change it, and I'm going to go back to using x's. We're going to change it by some amount x. But in this case, we have the stoichiometric ratio of 2 here. So this actually is going to change by a factor of 2x. So my equilibrium concentrations will be as follows. Now, because of this stoichiometric 2 here, that makes my KSP equal to the concentration of my copper ion times the concentration of my hydroxide ion squared. Remember, that value there needs to be the exponent in my equilibrium expression. So now I can fill in my numbers. 2.2 times 10 to the negative 20 equals x times 2x squared. So I'm looking at actually 4x, so that would be 4x squared times x, 4x cubed equals this value, 2.2 times 10 to the negative, my 0 dropped off, 10 to the negative 20. So what I end up with is I need to take the cube root of 5.5 times 10 to the negative 21. And when I do that, the cube root is 1.77 times 10 to the negative 7, and that is the value of my x. Now the molar solubility is going to be related to that x. So I'm going to take that x, 1.77 times 10 to the negative 7, and that is moles per liter because we just calculated a concentration. And I'm going to multiply it by the molar mass. Now the molar mass of copper hydroxide is 97.57 grams per mole. So you see my moles cancel out and I'm left with grams per liter. So it is 1.7 times 10 to the negative 5 grams per liter. That is the molar or the solubility of copper hydroxide. So working with the same numbers, but working it a little bit differently. If the solubility of calcium sulfate is measured experimentally and found to be, here we go, 0.67 grams per liter, calculate the value of KSP. Well, I know that the value of the KSP is going to be related to the concentration of calcium and the concentration of sulfate. Now here I have the solubility in grams per liter, so I'm going to work backwards. And what I'm going to do is I'm going to divide it by the molar mass of calcium sulfate, which is 136.2 grams per mole, and this is calcium sulfate. And then I end up with a concentration, and that concentration is 4.9 times 10 to the negative third moles per liter. So I'm working backwards here. So here, I really don't need the ice, I just need the equilibrium. The equilibrium concentration of my calcium sulfate is 4.9 times 10 to the negative 3, capital M molarity. That is also the concentration of my sulfates, 4.9 times 10 to the negative 3, capital M molarity. So my KSP value is then calculated to be 2.4 times 10 to the negative 5. Again, we were given the solubility and we back calculated, we went backwards. We divided that solubility by the molar mass of the item at hand of the compound, calcium sulfate, and got the equilibrium concentration. That's what this represents. That's the concentration of the ion in equilibrium. Because this is a one-to-one relationship, it was very easy to do. We just plugged that into our KSP expression for the concentration of each of our ions in order to find the KSP. In Chemistry 1, you were presented with a number of different chemical reactions, and one of those types of chemical reactions was a precipitation reaction where you use the solubility rules in order to determine if a solid would be formed, if there would be a net reaction. Now, for the dissociation of an ionic solid in water, the solution is either going to be unsaturated, saturated, or supersaturated. And what we're going to do is calculate a Q in order to figure out if you will get a solid to form. Now, remember the Q value, just like in the last chapter, the Q value is based on some specific conditions. If Q is less than KSP, there will be no precipitate because there will be a few more ions that can be fit into the solution. If Q is equal to KSP, again, no precipitate will form. Q must exceed KSP in order for the precipitate to form. So if we're going to predict whether a precipitate will form with each of these conditions, we're going to look at, so what I need is the KSP of potassium sulfate and barium chloride. So I'm looking at the reaction between potassium sulfate, and I'm going to put my phases in here on purpose, and barium chloride. These are both soluble. I need to recall where my solubility tables are, and if you don't know where your solubility tables are, in order to predict whether or not you will form a precipitate with either of these compounds, you can look up the KSP because this compound has a KSP value, this one does not. Therefore, I'm going to say this one's going to be our most likely solid and this one's going to be spectator. This one's going to remain aqueous. So the KSP value of barium sulfate is 1.1 times 10 to the negative 10. So if I start with 0.080 moles per liter, and I have that many liters, what I want to find out is how many moles I have. So I have of sulfate, I have 0.052 moles of my sulfate, and that's found by taking the concentration of the potassium sulfate. Remember, this is aqueous and therefore it's going to break up completely. So 0.080 moles per liter times the volume, 0.650, and I get 0.052 moles. Now I need to divide that by my total volume. I hope you're seeing a theme here with total volume, so that I get a concentration of my sulfate of 0.058 capital M molar. Now I need to look for my barium. My barium is going to have, we're going to do a similar calculation, 0.0040 moles per liter times the volume, 0.250 liters. And I get 1.0 times 10 to the negative third, and that is moles. That's moles of barium. What I'm doing is calculating my barium concentration for this particular solution. This was my sulfate concentration. And I get a value of 1.1 times 10 to the negative third, capital M molarity. So now I'm going to analyze my barium sulfate, and I'm looking for my Q value, which is equal to my barium concentration times my sulfate concentration. And in this case, I'm going to multiply these two numbers together and I get a Q value of 6.4 times 10 to the negative fifth. That's my Q value. So now I need to compare that to my K value. And in this case, the Q value is much greater than the KSP value. Therefore, yes, there will be a precipitate. And there will be a precipitate because Q is greater than KSP. We have more ions in solution than the KSP will allow. Therefore, we will have a precipitate. For B, we have again our potassium sulfate and silver nitrate. Now, there is a KSP value given for silver sulfate, which is one of our potential, and this is Ag2, silver sulfate. And that KSP value, it would be equal to the concentration of the silver squared times the sulfate. Remember, silver is commonly silver 1, and this is the value given, or this is the compound given in the KSP table. In case you need to double check yourself, these things are given to you if you know where to look. So because this is my KSP expression, now I need to calculate my values of concentration of silver and my concentration of sulfate. Now my concentration of sulfate is going to be similar, or actually both of these concentrations will be calculated similarly to the way that I calculated the concentration previously. So what I'm going to start with is the concentration of my sulfate in moles per liter multiplied by the volume. I'm going to move my KSP here. And then that's moles of sulfate divided by my total volume. Now my total volume here is going to be 0.650 plus 0.175 milliliters. So I get a total concentration of sulfate in this case of 0.0063 capital M molarity. Now for my silver, again, you take the volume given of silver times the concentration divided by the total volume of the solution. And I get a concentration of 0.0032 molar. So now we look at the KSP expression for silver nitrate. Now, remember, our silver concentration needs to be squared, and our silver concentration needs to be squared because silver nitrate or silver sulfate forms 2 silver 1 ions and 1 sulfate ion. Remember that this stoichiometric equivalent here needs to be used as the exponent. So when I fill in these numbers and do the appropriate arithmetic, so it ends up being 0.0032 squared times 0.0063, then the KSP, or the Q value, because what we're doing is calculating Q once we add in these non-equilibrium concentrations, my Q value then equals 6.5 times 10 to the negative 6. Well, my KSP for silver sulfate, I looked it up, is 1.5 times 10 to the negative 5. So because Q is less than KSP, there will be no precipitate. And you should understand this conceptually, that there can be more of these ions in solution before KSP is like the threshold. When you exceed that threshold, that's when you start to fall out of solution. The solution can hold a few more ions than we've given it, so there will be no precipitate. Now, you'll be asked eventually to qualitatively determine the solubility of an ionic compound, and there are several factors that can determine that solubility, and one is the common ion effect. So, for example, adding the conjugate base or a salt to a weak acid is similar to the common ion effect. pH can affect the solubility of an ionic compound as well as the formation of complex ions. So if we're going to calculate the molar solubility of silver chloride in a solution that is 6.5 times 10 to the negative 3 moles of silver nitrate, now what we're going to do here is we're going to analyze silver chloride, which is a precipitate, a solid, and it has a KSP value. So we need to know the KSP value of silver chloride. And that KSP value is 1.6 times 10 to the negative 10. Now you also need to know that silver nitrate will completely dissociate. It is an ionic compound, it's a strong electrolyte. So when it dissociates, when I have my silver nitrate, it completely dissociates into silver and nitrate, and these are all aqueous. Therefore, If we have 6.5 times 10 to the negative 3 silver nitrate, that means we also have 6.5 times 10 to the negative 3 silver, and that's what we're starting with. So now what we have is a start for our KSP expression. So if I have a solution that has some silver nitrate in it, and I start with a little bit of my silver, so I have my initial, then I'm going to change. I'm going to add to it some amount, and I'm going to use X, although your book wants to use S. So my equilibrium concentration will be 6.5 times 10 to the negative 3 plus X, and X for my chlorine. So if I plug those values in to my equilibrium here, or my KSP, then I can solve for X using all of the appropriate algebraic. I can solve for X because I can simplify this X because my initial concentration and my KSP are more than 3 orders of magnitude different, more than 1,000. So I can solve for my X very easily so that X equals 2.5 times 10 to the negative 8 capital M molarity. The molar solubility is then equal to this X. We were not asked to find the solubility, but the molar solubility. So we need to have a mole in it. So the molar solubility of silver chloride in a solution that is 6.5 times 10 to the negative third moles of silver nitrate is 2.5 times 10 to the negative 8. Now, pH can affect the solubility of a substance as well. So if we consider the solubility equilibrium of magnesium hydroxide, which is up here. Now, according to Le Chatelier's principle, if we add hydroxide ions by increasing the pH, so if we add here, we will shift towards the production of more of our solid. So this is also kind of a common ion effect because we're adding a common ion. So to see how this affects solubility, here's our KSP equation. And what happens at equilibrium, so our S is equal to 1.4 times 10 to the negative 4. So at equilibrium then, the concentration of hydroxide equals 2.8 times 10 to the negative 4. And the pOH, 3.55, the pH is 10.45 at equilibrium with solid magnesium hydroxide. So in a solution with a pH less than 10.45, the solubility of the magnesium hydroxide will increase because if the pH is less, that means we have less hydroxide ions. We would increase the production. So, and that works because if I'm going to add an acid to this solution, then what I'm forming is more magnesium ions. So if the pH were higher than 10.45, then that would decrease the solubility of magnesium hydroxide because of the common ion effect. So again, for example, barium fluoride. Here, if we add hydrofluoric acid, then we remove the fluorines from the net reaction. By adding the acid, we increase the concentration of the barium, but we decrease the fluorine. Now keep in mind that the solubilities of salts that contain anions that do not hydrolyze these are not affected by pH. So which of these compounds will be more soluble in an acidic solution than in water? Well, let's look at copper sulfate first. So copper sulfate dissociates into the copper or copper sulfide. There we go. Sulfide makes more sense. Now, sulfide is the conjugate base of the weak acid hydrogen sulfide. So the hydrogen sulfide, so our sulfide will react with acid to form this. Now, because of that, this copper sulfate will be more soluble in acid. Now for B, looking at silver chloride, remember silver chloride goes to form silver and chlorine. The chloride ion is the conjugate base of a strong acid, hydrogen chloride or hydrochloric acid. So it doesn't react with hydrogen, and therefore it is no more soluble. The solubility does not change in an acidic solution. But for C, we have lead sulfate. Now, lead sulfate reacts to form lead and sulfate. That makes more sense. Remember, this is sulfide, this is sulfate. Now, the sulfate, that is a conjugate base of that acid. And because of that, and this one isn't the strong acid. This is. So because of that, because it's the conjugate base of a weak acid, this is more soluble in the acid. Complex ion formation is something I want you to fundamentally be aware of, but we're not going to harp on a whole lot. Those of you who might be chemical engineering students might need to know a lot more complex ion formation, in which case you will likely have an additional class that really focuses on these. But a complex ion is an ion that contains a central metal atom, like here, that is bonded to one or more molecules or atoms. So it's a complex molecule. Cobalt chloride is pink because of the presence of a hydrated or complex cobalt ion. When hydrochloric acid is added, there's a change from pink to blue. And that's because the blue is the cobalt chloride. The chlorine has removed the hydrogen from the cobalt. When we look at the formation of these ions, we express them like this. And remember, these are complex ions, so they will have a charge to them. And they have a K of formation. Of course they do. And those Ks of formation will be provided to you or in a table. You do not need to memorize any of these K values. Now, the K expression is built the same way any of our other K expressions are built. The solids here are these are the parts of reactions, and this is the net. The solids cancel out so that what you're left with are the aqueous, and here your hydroxides cancel as well. So this is your net reaction, and the net reaction is the K of formation. I'm not going to add problems like this to the quiz, so I'm not going to go over this worked example. I think there's enough going on in this chapter that I really want to focus on with the acid-base equilibria and the buffers that I'm not going to dive deep into the complex ion formation. We can use a technique called fractional precipitation in order to separate mixtures based on solubility. Now, we use this actually in industry. I was specifically on a job with offshore drilling where we were removing silver from the wastewater. And we used this fractional precipitation in order to reclaim our silver. Now, if silver nitrate is added slowly to a solution, that is 0.020 molar in chlorine ions and 0.020 molar in bromine ions, calculate the concentration of silver ions required to initiate the precipitation of silver bromide without precipitating silver chloride. Well, this is one of those fun calculations that you can see how the math relates. So because the formation constants are, so we need to look at the differences here between our silver sulfide and silver bromide. So the silver sulfide, of course, forms our silver and chlorine ions. I'm going to leave the phases off. Silver bromide forms silver and bromine. They're all the same charge. Now the KSP of silver chlorine or silver chloride is 1.6 times 10 to the negative 10. The KSP of silver bromide is 7.7 times 10 to the negative 13. Now, because the KSP for silver bromide is much smaller, this is a much smaller number, the silver bromide should precipitate first, and so it will require fewer silver ions. So if we solve for silver by using the KSP expression, and I would solve for silver by saying 7.7 times 10 to the negative 13. Now I have a concentration of bromine ions, and the concentration I'm just going to fill in here at 0.020 capital M molar. So I can solve for my silver, and the concentration of my silver ions is 3.9 times 10 to the negative 11th capital M molar. And that would form a precipitate. So we must have more than 3.9 times 10 to the negative 11. Remember, when Q equals K, we have no precipitate. So we need more than 3.9 times 10 to the negative 11. But we cannot exceed what it would be for K for silver chloride. So if this is the amount of silver to remove the bromide, we need more than this. Then to avoid coming up to precipitating the chlorine, I can find if Q equals the KSP now, which is 1.6 times 10 to the negative 10, and I solve for the silver ion, and I have my chlorine ion, I can solve for my silver ion in this case would be equal to 8.0 times 10 to the negative 9 capital M molarity. So for the silver chloride not to precipitate, I must stay below this number. So if I'm calculating the concentration required to initiate the precipitation, then my concentration of silver must be below 8.0 times 10, I'm running out of room, to the negative 9th, and must be greater than 3.9 times 10 to the negative 11. Using selective precipitation is a common technique in general chemistry laboratories where we can determine the identities of metals based on what precipitates. So if we have a solution containing ions of all cation groups and we start with hydrochloric acid, if we get precipitates, we know we have either silver, mercury 1, or lead. So whatever does not have the precipitate, whatever is left, we then add our hydrogen sulfide. And then if we have a precipitate, we know we have one of these metals. So then to whatever solution is left, we add sodium hydroxide. And then we know if we have a precipitate, we have one of these metals, and so on. So we use selective precipitation in the laboratory an awful lot. Now there is a lot going on in Chapter 17. The common ion buffer, solutions, Henderson, Hasselbalch, the titrations, acid-base stuff, all of that can really be lumped together. That would be like general topic number 1. Then we start talking about solubility, and that solubility would be general topic number 2. And then this complex ion formation and stuff, I'm not really know what it is. That's a concept or a reading question. That's not going to be a calculating question for you. Fractional precipitation qualitative analysis, I could call that number 3, but that's more like a 2A. If you're only going to focus on one general thing, focus on this business right up here. This is where the majority of your calculations are going to be, and that is where the majority of the entire chapter really is. So if you really only have time to focus on one set of stuff, focus here. A lot of the calculations are similar to what you've seen in Chapter 16, so it should come fairly easily. As always, if you have any questions, please let me know.